Okay. All right, so to figure out U2, U1, let's take a look at the context of the problem again. In this problem, we're told volume and temperature of state 1 and volume and temperature of state 2. Okay? And so in this problem, we know information about volume and temperature, right? And what we want to figure out is this internal energy. So what we're going to do, so from problem, we know info about volume, molar volume, or volume in general. We could calculate the molar volume by just taking the regular volume and dividing it by moles. Okay? So we know those pieces of information. And so what we're going to do is we're going to describe our internal energy as a function of molar volume and temperature. So we'll call it U, molar U, as a function of molar volume and temperature. All right, so that's what our function is going to be. What we're going to do now is we're going to take the total derivative of U. And when we take the total derivative of it, so what I'm saying here is that for U, we're going to say that V and T are the canonical variables for it. And so when we take the total derivative of it, we're going to write it in terms of its partial derivatives. All right. So that's just, the total derivative written in terms of its partial derivatives. This is just, writing it exactly as math would tell us how to write it. Okay? Now that we wrote out the math, let's start applying, the context of the problem, the physics of the problem. All right, so in our problem, we're doing an isothermal compression, right? And so if the system is isothermal, that means that the changes in temperature are 0. So this term on the right, second term on the right-hand side, is going to go to 0. Okay? And so what we're left with is just this first term in our total derivative. And so if we wanted to figure out the difference, or delta U, so U2 minus U1, to figure that out, all we would have to do is integrate our total derivative from state 1 to state 2. Right? And if we're integrating the du from U2 to, or U1 to U2, then we would have to integrate the right-hand side as well. And we're integrating it with respect to molar volume. So we would have to go to molar volume 1 to molar volume 2. Okay? All right, and so integrating this just gives us that. But on the right-hand side, this looks a little bit weirder, right? Now we're integrating a partial derivative. And what exactly does that mean? In fact, how exactly is U a function of V? How are we going to integrate that? All right, a couple of things I want to point out. First, I want to emphasize this is molar volume. So to get the molar volume, you would take the actual volume, which in state 1 it was 100 liters, and we would just divide that by the number of moles. So this would give us 20 liters per mole. All right, but in any case, we want to do this integral, and we want to integrate this thing. But what exactly is it? And that's where all that calculus of thermodynamics we did in problem 1 comes in handy. Because in problem 1b, we demonstrated this, or we proved this, that our partial derivative of u with respect to v at constant t, we could rewrite it like this. Okay? Right? So without making any assumptions, we just said this was equal, we showed that this was equal to this. So please review the problem 1 solution if you don't remember exactly how we did that. In any case, so we showed that this is equal to this, and so what we could do is we could just take this and plug it in here. So let's plug that in. So u2 minus u1 is equal to the integral from molar v1 to molar v2 of t partial derivative of p with respect to t at constant volume minus p dv. Okay? Alright, so to figure out our difference in internal energy, we would have to go through this calculation. Right? Now we still have this partial derivative in here, which looks kind of weird, but it's actually not that big of a deal. Because what we have here, we have the partial derivative of our pressure function with respect to temperature at constant volume. Alright? And so if we had some sort of equation that described pressure as a function of temperature, what we would be able to do is we could just plug that in here, go through that derivative, then get a result, and then integrate that result. And so what we need to do at this point is we need to plug in our different equations of state, or different pressure equations of state, in order to actually calculate a value for u2 and u1. Okay? Alright, and so let's go out and do that. So, to demonstrate this to you, let's first start with the simplest equation of state that we know of, which is the ideal gas law. So from the ideal gas law, we know that pressure is equal to nRT over V, and we could also write it in terms of molar volume as well, where this just moves down here. Okay, so that's the ideal gas law. And so, if we took the partial derivative of the ideal gas law with respect to temperature, what we would get is dt over dt constant V, and this is just 1. And so we find that dp over dt constant V is just R over V. Okay? Alright, so now that we have the result, let's go back to what I'll call equation 3 and just plug that in. So then we have T times our partial derivative from the ideal gas law, which ended up just being R over V. And we're going to subtract off of that pressure. And from the ideal gas law, we know what pressure is. RT over V. Okay? And as you can see, this first term is RT over V, and the second term is negative RT over V. And so what we get in the end is just 0. Okay? Alright, and so for the ideal gas law, we showed that the change that if we have an isothermal system, the differences in the internal energy are going to be 0. So this is the same exact result that we assumed before. But now in this case, we showed it without really making any assumptions, other than just assuming that pressure follows the ideal gas law. All right. And so here's, this is the reason why we can make that assumption, that if we have an ideal gas and it's isothermal, that the change in internal energy would be equal to 0. It's because of this sort of proof. Okay, so that's the result for the ideal gas law. So that's the simplest equation of state that we could deal with. But now let's look at a more complicated equation of state, specifically the van der Waals gas equation of state. All right, and the reason why we want to look at this more complicated equation of state is because it actually accounts for the physics of the molecules in our system. Specifically, it accounts for the fact that our molecules have some sort of size, and also that our molecules can interact with one another. I mean, it's still a fairly simple model, right? Because both A and B are treated as constants, which is not necessarily true in real-life systems. But at least for now, we could go through applying the van der Waals gas, because it will at least give us some qualitative observations in how internal energy, work, and heat would be affected. Okay? In any case, so with the van der Waals gas, we're now saying that pressure follows this equation. Okay? And so, let's go out and take the partial derivative of it with respect to temperature at constant molar volume. All right, in the van der Waals gas, the only term that has temperature is this first term. If we take the derivative of the second term with respect to temperature, that would just go away and be 0. So the partial derivative of it, of RT V minus B minus A over V squared, I think there should be squared. Okay? If we took the derivative of that, we would just get R over V minus B. That's what the derivative simplifies down to. So we can now take that partial derivative and plug it back into our equation 3. So here we had T times this partial derivative. So it's just going to be R V minus B. And then we're subtracting off pressure, which we know is this. Okay? All right. And so in this form, these terms are going to cancel out with one another. And so what we're going to be left with is this. That the difference between U2 and U1 is just going to be equal to the integral of the attraction parameter over molar volume squared. Okay? All right, so let's integrate that out. So when we integrate, we're going to get negative A. We could factor that out. It'll just be 1 over V2 minus 1 over V1. All right. And what we could do here, since we wrote this in molar volumes, if we wanted to, we know that molar volume is just regular volume over N, and the number of moles in our system is constant, so we could factor that out as well. So 1 over V2, 1 over V1. Okay. Though if you wanted, you could still do the calculation even in terms of molar volume. I just factored out the moles here just to make it a little bit more straightforward. All right, and so our difference in internal energy just ends up being this equation here. right? And so this is just, what the form would look like for the van der Waals gas. At this point, what we could do is we can now start putting in or plugging in the different values that correspond, the different van der Waals gas parameter values, the A and B, that correspond to different gases. All right? So, for example, if we're dealing with nitrogen, we know that that A parameter was 1.4 liter squared per mole squared. And I think there's a bar here. Okay? All right, so if we plug that in to our U2 minus U1 equation, what we get is negative 1.4 liter squared bar mole squared times 5 moles, and then times 1 over V2, which was 15 liters, minus 1 over V1, which is 100 liters, and then we need to do some unit conversion as well. Okay, so to do this unit conversion, I want to get rid of those bars. So I'm just playing around with units here. Okay? Alright, and in any case, by doing that, because I kind of want the final answer in joules, so I just took the gas constant written in terms of joules and divided it by the gas constant written in terms of liter bar, right? So that's essentially just taking gas constant divided by gas constant. So that's 1, but here I'm just playing around with units. Okay, in any case, what we get is U2 minus U1 is then equal to minus 40 joules per mole, right? Which is definitely not 0. So the ideal gas law for an isothermal compression, we would see that the internal energy would be 0. The difference in internal energy would be 0. But if we're dealing with a van der Waals gas, we see that if we do this isothermal compression, the system actually loses energy, even though it stays at the same temperature. Okay? All right, so just remember that for later. In any case, we figured out U2 minus U1. What I want to do now is I want to figure out the work term in our energy balance. And to figure out work, what we want to do is we want to take the pressure term and we want to plug in the van der Waals equation of state. So W is equal to V1, V2, P, dV. All right, and here I'm actually going to rewrite this in terms of molar volume just to make the math a little bit easier. So to do that, we pull out the moles from dV so that we get NP molar dV, or D molar V. Okay. All right. So now let's plug in the van der Waals equation of state. We'll go through the integral, and if we go through that integral, we get this natural log of V2 minus B over minus B plus NA 1 over V2 minus 1 over V1. Okay? All right, and so, once again, to calculate molar volume, we would just take the actual volume and divide it by N. All right, and so we know all the values in this equation. So if we plug in, we find that the work required for this isothermal compression is 24,000 joules. And it's a positive number, and that makes sense because we're compressing the system. So we have to add energy to the system. Okay, and so now that we have work and the change in internal energy, we could go back to our energy balance, and what we have is Q is equal to N U2 minus U1 minus work, and so that's equal to 5 moles times negative 40 joules per mole minus 24,000 joules. And what we find is that Q is then equal to negative 24,200 joules. And it's good that it's negative, because that means that this heat is leaving the system. Which matches what we would expect based on what we've seen before. Okay? Alright, so this is the heat that we calculate leaving the system if we're dealing with nitrogen gas. Okay? And specifically for nitrogen gas, it has a specific A parameter and a specific B parameter. But what we could do now, and the nice thing about using these kind of more sophisticated equations of state, is that with the ideal gas, it was just a function of temperature, volume, and moles. There was really no information or any parameters that would tell you that would be unique to different chemicals. But with the van der Waals gas, now we have these A and B parameters, which are unique to different chemicals. And so, with this equation of state, what we could do now is we can now look at how our system is going to be affected if we use different chemicals. So for instance, let's now look at a carbon dioxide gas, okay, where A is equal to 3.66 liters squared bar mole squared, and B is equal to 0.38 liters per mole. Okay. If we go to the U2 minus U1 calculation, the form of the equation would be the same, right? Nothing would change about our derivation. Oh, whoops, this is regular volume. Right, but the only difference here is now our A parameter is different. Okay. And so we have a different A parameter, and so if we plug this in, what we see is that the change in internal energy of our system is now minus 104.6 joules per mole. For nitrogen, it was only minus 40. But for carbon dioxide, we see that we get an even more negative number. Right? So that immediately shows us the utility of using the van der Waals gas. We see, or shows us how the system is affected if we use different gases. So we see a bigger drop in internal energy. And for the work, it's also still the same equation. But now the only differences are the B parameter is different, and once again the A parameter is different. And so in order to compress carbon dioxide from volume 1 to volume 2, so same volume and temperature as we did for nitrogen, we see that it actually requires more work in order to do that same compression. Okay? And in the end, in order to do this isothermal compression from the same volumes, keeping it at the same temperature, we see that if we switch out nitrogen with carbon dioxide, that the heat that needs to leave to the system is now larger in magnitude. Is lost than 4 and 2. And And so, if we do this analysis with the ideal gas law, it's independent of the chemical that we pick. In all cases, we would just get that internal energy is equal to 0, and that Q was just minus work. But now that we applied the van der Waals equation of state, we see that we could actually look at how different sorts of chemicals affect our analysis or affect our system.